When it comes to astronomy, it's easy to get lost among the stars and planets and galaxies, some of the biggest things in the universe. But small things can be important too. So some astronomers spend their time way down at the smallest subatomic level studying some of the tiniest known particles, like neutrinos. Neutrinos are tiny, electrically neutral particles that are produced by extreme nuclear reactions, like those that happen in the core of the sun or an exploding star. They are so small, in fact, that there are actually trillions of neutrinos passing right through the Earth, and you at any given moment, including right now, and now, and now. But despite their prevalence, they are really hard to find. Not only do they have 1,000,000 times less mass than an electron, which is an extremely unmassive particle, neutrinos also have no electric charge, so they don't interact with charged particles in any way. So astronomers have built enormous detectors all around the world in an effort to catch a handful of these things at a time. Why? Well, because neutrinos are the most direct way to learn about reactions that are happening deep inside of objects that we cannot observe firsthand, like the core of the sun, or supernovas, even black holes. Celestial objects like these all have one thing in common: lots and lots of energy, which results in plenty of intense nuclear reactions. And different kinds of nuclear processes produce different kinds of neutrinos. We've learned enough about neutrinos over the years to figure out which kinds are formed by which types of reactions. The trick is just spotting them. Luckily, neutrinos can be detected. When they buzz by particles like protons or electrons in just the right way, they produce distinctive flashes of light, called CHERENKOV radiation. In order to detect these tiny flashes, scientists set up huge tanks filled with a transparent medium and then surround them with light-sensitive detectors. Now, they can't just fill these tanks with air, because neutrinos don't produce enough energy to create that flash if and when they happen to interact with atoms in the gas. But lots of kinds of liquids do the trick, so scientists often use water, mostly because it is cheap, transparent, and plentiful. And that's how scientists built KAMIOKANDE 2, a detector deep in an underground Japanese mine filled with more than 3,000 tons of water, which helped detect the first ever neutrinos from a supernova. On February 24th, 1987, astronomers spotted an especially violent type of supernova, called a core collapse supernova, just 168,000 light-years from Earth. During these kinds of explosions, about 10 to the 58 neutrinos are produced in just 10 seconds, blasting out in space before the light from the explosion can escape the disintegrating star. So scientists checked the neutrino detectors and found that they'd caught about 20 neutrinos from that supernova, all splattering in within a few seconds as the blast wave raced past Earth. This was a big breakthrough in our search for neutrinos. For the first time, we knew that we could actually detect such remnants of distant, ancient explosions, and the data helped scientists finally pinpoint the range of mass that these tiny particles had. But neutrinos can come from sources even farther away, like supermassive black holes and far-off galaxies. In these cases, the high-powered magnetic fields around black holes can throw nearby particles into overdrive. And if everything lines up right, these particles collide with gas clouds, producing neutrinos, some of which head straight toward Earth. Those exotic particles are among the types that scientists are searching for with ICECUBE, one of the biggest neutrino detectors on the planet. ICECUBE is actually a giant cube of ice in Antarctica, 1 cubic kilometer to be exact, threaded with more than 5,000 detectors that are super sensitive to CHERENKOV radiation. In 2013, ICECUBE detected 28 neutrinos, and each one had more than 1,000,000 times as much energy as the neutrinos created by the sun. Based on their incredibly high energy levels, most of them seemed to come from outside the solar system. Some even appeared to come all the way from outside our galaxy. Now, neutrino astronomers are looking to the future, with designs for even bigger detectors that can study more exotic phenomena, things with intimidating sounding names like neutron star collisions and dark supernova. So even though neutrinos are difficult to catch, the small handful that we capture here on Earth let us peer straight into the heart of the most energetic and violent objects out there in the universe. Thank you for watching this episode of SciShow Space. If you'd like to keep exploring the universe with us, you can go to youtube.com/SciShowSpace and subscribe.